the domain of branching, so the branching Levy processes. Then discuss a little bit stable branching Levy processes, which is a class of branching Levy processes with a particular structure. And then I'm going to talk a little bit of what I announced in my slides, which is the fixed point of the branching convolution operation, so point measure which are invariant under the action of branching. Okay, so let me start by defining the space of random point measures. Sorry, the space of point measures, which is P, is the space of measures that can be described as a sum of direct masses with the largest element, and the sequence of direct masses go to -infinity. So you can have finite or infinite point measure there. If you have a finite point measure, you just set xk equals -infinity for all k large enough, and you discard all the atoms that are at position -infinity. Then on this space P, we can define the translation operator, which takes a real number x and translate every mass in the point process by x. So the tau xd is the sum of tau x plus xj, where xj are the position of the atoms of the point measure d. So then, okay, so we can start discussing about the branching random walk, which is the analogous in the space P of random walks. So this process starts with a unique individual at position 0 at time 0. And this individual gives birth at time 1 to a certain number of offspring, which are distributed according to a random point process. And then, independently, each of the children of that particle, they will give birth to independent copies of the same point process, shifted by the position of their parent. So every offspring gives birth to, every particle gives birth to children around its current position, independently to everyone in its generation, as well as to all other generations in the process. So you have the process that can keep growing like this over time. And what we will take interest here are okay, Zn, which is the sequence of point measure. So I will completely forget about the genealogical structure that is apparent in the construction. I just look at the sequence of a set of point measure at each time. So, okay, so more formally, we can define the branching random walk like this. So it's quite classical to have this integrability condition over there. So this exponential integrability condition, it is very helpful because it guarantees that the process does not explode, and that with this condition, you know that Zn is indeed a Markov process that lives in the space of random point measure with a maximal element. So it's quite helpful in these settings to introduce the branching convolution operator. So similarly to the convolution operation that allows you to describe the law of a random walk after n step, you can define the branching convolution operator, which allows you to describe the law of a branching random walk after n step. So I write this d ast e, which is what happens when you make one step of a branching random walk with law d, followed by a step of a branching random walk with law e. So indeed, the initial particle makes children according to the law d, and then each child make an independent copy of the process e, but shifted by the position of its position. So obviously, this is not an abelian operation, right? You cannot d ast e is not the same as e ast e. So this operation indeed allows you to describe the law of the branching random walk at time n. So I write the ast n, the nth iteration of the branching convolution operator on the variable, on the law z. And there is immediately a small problem related to this branching convolution operator, is that it's not continuous for the topology of weak convergence of point measure. So for example, if you take Rn, which is a law where you almost surely put n particles at position minus n. Okay, so for each n, I put n particles at position minus n. So if I look in a closed neighborhood of 0, let's say, well, after some time, all my particles will disappear in Rn. So in some sense, I want to say that Rn goes to 0 for this topology, converge to the law of the empty point measure. And similarly, I can define Yn, which is a law where with probability 1 over n, I have one particle that makes a jump of size n, and with probability 1 minus 1 over n, I make no offspring. Then with the definition of the branching convolution operator, see that I want to say that Rn should converge to the law of the empty point measure. Yn should converge to the law of the empty point measure. But when I do the convolution between Rn and Yn, well, I have n particles, each of which having probability 1 over n to make a positive jump of size n. So we expect that this converges to a random number of particles at the origin after the exchange of those two conversions. So there is no continuity for the branching convolution operator, which was quite bothering at some times. Okay, yeah, okay, sorry. So here is the graph for 3 classes that are closely connected in Levy processes, right? So you have the space of infinitely divisible distribution, which are the variables that can be written as the value at time n of a random walk for n. You have the space of Levy processes, which I already discussed, and the Levy-Kinging exponents, so the particular form that takes the Fourier transform of the law of a Levy process at time 1. So in the branching world, okay, the infinitely divisible distribution will be replaced by the infinitely ramified point measures. The Levy processes will be replaced by branching Levy processes, and we will have like characteristic triplets, so sigma squared A lambda, to describe the law at time 1 of a branching Levy process. So the particular difficulty in this diagram is that, contrarily to what happens for the Levy processes, we no longer have access to the Fourier transform. You can do the Fourier transform of a random variable, but for a random point measure, you cannot just do a nice computation like this. And the branching convolution operator, when you apply it to Fourier transform of functionals of a point measure, it does not become equivalent to an exponentiation of the Fourier transform. So there are some difficulties there. Okay. So what is an infinitely ramified point measure? So just to mimic what happens in the real value for the real valued random variables, an infinitely ramified point measure is a point measure that you can represent as the value at time n of a branching random walk, no matter what n is. So in other words, a law z is infinitely ramified if no matter what n is, I can find a law dn, so that if I apply n times the branching convolution operator to dn, I get the law z. So, okay, so let's make a small picture maybe. So here is a random point measure. I say, okay, so it can be represented as the value at time 1 of a certain branching random walk, and as the value at time 2 of a branching random walk, and as the value at time 3 of a branching random walk, and so on and so forth. So this is an infinitely ramified point measure. How many did I put? Encore? Okay, good. So now branching Levy processes, my second object. So branching Levy processes will be a Markov process in the space of McAlpy of point measures, which is right continuous for the right topology, and so that whatever the value of t, the process zt, z2t, z3t, z4t, etc., is a branching random walk. So another way of saying this is to say that a branching Levy process is a right continuous process that satisfies the branching property, so that whatever time s and t, zt plus s is given by the sum for every atom in zt of independent copies of the s translated by the position of the atom in ZT. So here, some results that we prove with Jean on these processes were that, well, first, if I have an infinitely ramified point measure, then I know that there exists at least one branching Levy process, so that the law at time 1 of that branching Levy process is equal to the law of this infinitely ramified point measure, provided that you have some exponential moment. And a second result was that the law of a branching Levy processes is characterized by a triplet sigma squared A lambda, where sigma squared is a non-negative real number, A is a real number, and lambda is a sigma finite measure on the space T that satisfies some integrability condition that reminds a little bit of the integrability condition that we ask on pi. And this sum of e to the theta xk minus 1 minus theta x1 is just something that allows the branching Levy process to have an exponential moment of parameter theta here. That the expectation of the sum for all atoms in the process at time 1 of e to the theta xk as finite mean. Okay, so you see that it's not exactly as what happened in branching in Levy processes. Here, I do not have a one-to-one map between infinitely divisible distributions and branching Levy processes. So it is not clear for us if, for example, there are different values of sigma squared A and lambda that give birth to the same value at time 1 of the point. It was a major difficulty for us to link this triplet to the law of the branching Levy process at a finite time. And it's very problematic because there are a lot of nice results that are known for branching random walks. And those results on branching random walks are usually done under some integrability condition regarding the law at time 1 of the branching random walk. So if we want to export those results to branching Levy processes, well, we have to translate this integrability condition on the branching random walk to integrability conditions on lambda. And let's say the dictionary that allows to make the translation between the two is still being written. So yeah. Yeah, here. So for example, here you don't have a Levy-Ito decomposition. Yeah, we have a Levy-Ito decomposition for the branching Levy process, right? So that's exactly what I'm going to do here. So describe the Levy-Ito decomposition. So given sigma squared A lambda, how do I construct a branching Levy process which has these characteristics? So that's what I'm doing here. So I first do it under the assumption that lambda is a finite measure. Okay, so not exactly lambda is a finite measure, but where the lambda put finite mass on the set of point measure with not one atom, right? Either 2 or more atom or 0 atom, this quantity has finite mass. And I have a first moment condition additionally to ensure that the process does not explode in finite time. So then, in this situation, this branching Levy process can be described simply as a kind of generalization of the branching random. So you start with a particle alive at time 0. This particle will move according to a Levy process for some time, which is an independent exponential time. And after the independent exponential time, the particle will die, giving birth to a certain number of offspring that are positioned around its death time. So it's quite a natural definition for a branching Levy process, right? You move as a Levy process, and after some time, some independent exponential time in order to have a Markov process, you die and you give birth to offspring that are positioned around your current position. Okay, and then you start over again and again. Every particle moves independently and gives birth to offspring independently. So what is the relationship between the parameters of this description and the triplet sigma squared I lambda? So the Levy process that gives the motion of the particles is sigma squared A pi, where pi is the measure lambda restricted to the space where you have only one atom that is not equal to minus infinity. So lambda, when you have no more than 1 point, it is just the jump rate of your mother particle. And when there are 2 particles or there are 0 particles that are alive, then lambda describes both the rate at which you create k offspring or you die out, and the distribution of the offspring. So lambda is a joint information on the jump rate of the particle and the way offspring are generated when the particle dies out. Okay, so now what happens when lambda is not a finite, a measure with finite intensity? Well, then we can define a restriction of lambda by erasing all the atoms in my process that are smaller than a fixed value. And for all value of k, I can construct a branching Levy process with this parameter k. But this can be done in a consistent way, where when I increase k, I just add more and more particles that were erased in the previous iteration. So you get a family like this of particles that grows, and you can define the branching Levy process with parameter lambda as the increasing limit of this family of processes. So a thing that does not that is not preserved by this increasing limit is the genealogical structure of the process, right? If I had made a better picture, I could have had the initial particle that dies at closer and closer times to the origin, right? The ancestor, the parent particle could die out in time almost 0. So in order to avoid this difficulty, you can always define the mother particle by saying, okay, I identify the parent with the leftmost child, and then you have like longer lifespan, so you can still talk about genealogy of the particles. So here. Okay, so some examples of branching Levy processes that are already well known. So the simplest branching Levy process, what can think of is a branching Brownian motion. So there, sigma squared is just the diffusion of the Brownian motion trajectories of particles, and the measure lambda will be just beta times the direct mass, where you put 2 atoms at 0 and no atom everywhere else. Then with this description, you just give that you have a particle system where particles move as independent Brownian motions, and at exponential times of parameter beta, they give birth to 2 offspring that are positioned exactly at the same position where their parents were. You can also have a branching Levy process with parameter 0, 0 lambda. Then you have particles that do not move, but they give birth to offspring according to the point measure lambda. Right? So for example, if lambda has finite total mass, after an exponential time of parameter lambda, the particle dies out and is replaced by an independent copy of a point process sampled according to the law lambda divided by its total mass. And if the point measure lambda always have just 1 atom, then the branching Levy process is just a Levy process. Right? You have a particle that moves but never split into more than 1 particle or die out. So you just have a Levy process. Okay. So once we have defined the class of branching Levy processes, one can take interest in the class of stable branching Levy processes. So to define this thing, we have to define the multiplication of a point measure by a constant. Right? I want to be able to speak about scaling limits of particles, so I have to have a way to multiply by some scale in order to talk about stable Levy processes, branching Levy processes. Sorry. So this is done. Well, we choose to do it this way. So okay, so I take lambda positive and d a point measure. Lambda d will be just the point measure that you obtain if you multiply every atom in the point measure d by lambda. Right, so I just make an homothéty on the point measure, and it gives me the image by the multiplication by lambda of that point measure. So then I can talk about stable branching Levy processes that are as branching Levy processes, which specifies the following equalities: that if I increase the rate of the time by parameter lambda, this has the same effect as dilating the branching Levy process by parameter C of lambda. Okay. So then, so when you bar degenerate cases, so for example, the empty branching Levy process is a stable process for all functions. The branching Levy process where you just have one particle that stays put at 0 for all times will be a stable branching Levy process. If you bar those two degenerate cases, C of lambda, this scaling constant, is uniquely defined for each lambda. And you have a nice property that C of lambda times mu has to be equal to C of lambda times C of mu. So there is necessarily an exponent for the function C, and C of lambda can be written as lambda to some power alpha. So I will define the alpha stable branching Levy process as a branching Levy process such that Z lambda t is equal in this solution to lambda to the power alpha times Zt. So it's quite analogous to stable Levy process. So then a joint result that we obtained with Jean and Acer Cortines was that when alpha is larger than 2, there is no non-degenerate alpha stable branching Levy processes. When alpha is between 0 and 2, there are non-degenerate alpha stable branching Levy processes, but those are just the alpha stable Levy processes. So when alpha is strictly positive, either you have no process or you have a process with only one particle. Branching is forbidden when alpha is positive. And okay, so when there is no non-degenerate zero stable branching Levy process, and for alpha strictly negative, there are stable branching Levy processes. So you have stable branching Levy processes with negative exponent, and those are given by branching Levy processes where particles never move, but they give birth to offspring at some according to some point measure lambda, which have a specific value. So it means that either in stable branching Levy process, either you can have children but not move, or you can move but not have children. And it's quite reasonable, right? Because if you scale time by a factor, if you shrink time by a factor, when alpha is positive, you bring space closer together as well, right? So if you were able to have more than one particle, then by this scaling factor, you would have an infinite branching rate at the origin. So in time 0, you would have an infinite number of particles everywhere on the real. And the same thing can be said when you have negative exponent, right? When you shrink time, you just dilate space. So if you were able to move a little bit, then by shrinking the process, you would have that maximum and the minimum increase. So actually, in time 0, you would move all the way up to plus or minus infinity and put mass everywhere again. Okay, so here is an illustration of a branching Levy process with a negative exponent. So since particles never move out, I just put the burst time, the burst time and position of the process in the square 0, 1. Okay, so here is the first few points. So I started on the top left corner of the screen, and this is the first generation. This is the second generation, the third generation, the fourth generation. So generation after generation, you see that more and more particles move out, and so you have to imagine that you are here, right? So for the stable branching Levy process, at every point you draw a line starting from that point and that survives forever, and gives you an idea of how does this process look like. So stable branching Levy processes have plenty of nice properties. For example, if you look at the additive martingales of stable branching Levy processes, no matter what the direction you look at, the law is the same. So you have a nice family of non-negative random variables that all have the same distribution, and this one parameter family is analytic, so it's okay, can be fun. So why do we take interest in those stable branching Levy processes? Well, it's because there are expected to be scaling limits of branching random walks. And that's exactly what Jean did with Young. I don't remember his first name, but okay. Well, not long ago, right? In March or April, something like this. So that if you have a branching random walk in some specific settings, you can show that the scaling limit of this branching random walk will be an alpha stable branching Levy process. So the scaling limit of branching random walks are branching Levy process. Okay. So now I'm going to speak a little bit more of the original topic of my talk, which was the fixed point of the branching convolution equation. So I introduced this branching convolution operator, and the question that we have been interested in for some time with Pascal Maillard was the study of point measures E, which satisfies the following properties that for some point measure Z, E is equal in distribution to the superposition of the point measures of RID copies of the point measure E shifted by the position of all the atoms in the point measure Z. So in terms of the branching convolution equation, I look at laws E such that E is equal to the convolution of Z and E. Right? So I say that my point measure E is the same as what happens when I make first a step of a branching random walk with reproduction law Z, then a step of branching random walk with reproduction law E. So why is this interesting? Well, it's because this type of point measures are the one we expect to observe in limits of extremal process of branching style structures. Right? If you have a spatial branching process, and you look what happens near the rightmost position after some very long time, well, you expect to see convergence to some point measure, and using the branching property of your branching type process, you expect that this point measure to be equal to what happens when you first make a step of your branching process, then independently, each of them will converge to same independent copies of this point structure. So it was interesting to take interest in that convolution equation. Okay, so I will make some assumptions on the point measure Z. So first, I will assume that it is supercritical, so that the mean number of points in the point measure Z is strictly larger than 1. So it means that if I start a branching random walk with a point measure Z, I have something that survives with positive priority. And I will assume that there exists some parameter theta strictly positive, so that the expectation of the sum of e to the theta zj is equal to 1. Okay, so this condition seems quite stringent, but actually, if you assume that the sum of e to the theta zj is finite, then if you replace z by z shifted by the log of the expectation of theta zj, you get something that looks like this. So it's not that an important condition. You just have to have some kind of a scaling factor, and here you do it like this. Okay. A second condition that will be important for it is a non-lattice condition. So we assume that there is no integer lattice on which the point measure z is supported. And last assumption is that we are either in the regular case or in the boundary case of the branching random. So the regular case, I ask that the sum of the zg e to the theta zg is strictly negative and larger than minus infinity, and some x log x integrability condition. And under this assumption, I know that the process integral of e to the theta x with respect to the m, so sum for all particles at the n generation of the branching random walk of e to the theta position of that atom. This is a martingale, right? It's a martingale because of the integrability condition that I have here. The expectation of e to the theta z1 is equal to 1. And under the assumption A3A, the martingale is non-degenerate and converge to a positive to a limit which is positive with positive priority. The other case will also work out. So if I assume that the expectation of the sum of zj e to the theta zj is equal to 0, but that I have some stronger integrability condition, so a finite variance term and an x log x squared type integrability condition, then this is not the integral of e to the theta x, which is a nice convergence martingale, but it is instead the derivative martingale, the integral of x e to the theta x against point measure Zn. And in both cases, those martingales, they will converge to a positive with positive priority finite limit. Okay. So A3 will be either A3A or A3B. Either we are in the boundary case or we are in the regular case. And then what we show with Pascal was that under those three assumptions, so supercriticality, non-latticeness, and regular or boundary case, then any point measure which satisfies E is equal to the convolution of the law Z with the law E can be described as a shifted, decorated Poisson point process with exponential intensity, with a decoration that is arbitrary, but with an intensity which is given by some constant, which is arbitrary, times S, the limit of the additive or the derivative martingale. So a point measure which can be described as a branching invariant can always be factorized as the convolution of a Poisson point process with intensity Cs e to the minus theta x with some other point measure. So yeah, still not, okay. Okay, so there is a problem here is that this convolution equation does not characterize at all the law of the decoration. So for example, if I take the law of the decoration, which is just a direct mass at 0, what I'm just saying is that the Poisson point process with intensity times S times e to the minus theta x are stable by the branching convolution operation. And any point measure that I put so that E convoluted with X is a point measure will be a branching invariant point measure. But what is interesting here is that, for example, if I look at the branching random walk seen from the extremal position at some very large time, we know that it converges to exactly that type of process, right? It converges to a shifted, decorated Poisson point process with exponential intensity. And the law of the decoration is always quite technical to obtain. And so, yeah, we expected to be able to say more things on this, but yeah, it seems we just reobtained things that were already known, at least in the settings of the boundary case. So what we would like to, sorry, I don't remember what I wrote. Yeah, sorry, yeah, okay. Again, so it's exactly the thing as I told you before, right? So if I assume, if I have a branching type process, and I know that the extremal process converges to something, then the limit has to satisfy the equation E is equal to the Z convoluted with E. So, okay, it does not help us when, with asymptotic behavior of the extremal process of the branching random walk. But for example, in time homogeneous settings, it has some nice applications. For example, there is this result by Mallein and Zaitouni, which gives the asymptotic behavior of the position of the maximal particle in a branching random motion, where the variance is decreasing over time. And they obtain a very nice estimate on the position of the maximum. Well, if we were able to prove that the extremal process seen around this maximum converges to some point measure, we would know that, well, the limiting point measure has to be stable by the convolution with a branching random motion with variance sigma naught. So I don't know what the limiting mode measure will be, but I know that it will be a Poisson point process with intensity, the derivative martingale of branching random motion with intensity sigma naught and exponential parameter with some decoration point measure. And so we don't know what the decoration point measure is, but we have a bit of the answer here. We're using this branching convolution equation. Okay. So how do we have some access to the decoration? Oh, no. Okay, sorry. So here I just give the step of the proof. So actually, the proof is quite easy because everything is already present in the literature. So you take a point measure such that E is equal in distribution to a step of branching random walk with low Z followed by a step of branching random walk with low E. And you look at a test function phi, and you define f phi of Z, which is the Laplace transform of phi applied to the point measure E shifted by Z. Okay, so if I know f phi of Z for a large enough class of function phi, I will have characterized the law of my point measure E. But due to the branching convolution operator, what I can observe is that f phi of Z is quite interesting, that f phi of Z is the expectation of the product of fi of Z plus Zj, where Zj are the set of atoms of the point measure Z. So in other words, f phi is up to a change of variable is a fixed point of the smoothing transform. Right? It's a function which is fixed point of the smoothing transform, and these functions are known. So, for example, the result of Altmaier begins and minus give all fixed point of the smoothing transform satisfying some properties, and which include the properties that satisfy my function f phi. And so they say that for all function phi, for all test function phi, there exists a constant C of phi such that f phi of Z can be written as the expectation of minus this C of phi times S, the limit of my martingale, times e to the minus theta Z. And then I use the result of Subag and Zaitouni, which tell me that, well, actually, if f phi of Z has this form over here, then I know that my point measure E is a shifted decorated Poisson point process with exponential intensity. And the law of the decoration is hidden in the constant C of phi. So if I can compute C of phi for a large enough class of functions phi, I have access to the law of the decoration. Okay. So there is also a recent result by Shen, Garban, and Shekal, who studied the dual branching convolution operation. So they look at point measures E, so that E is equal to E convoluted with Z. So in other words, I start my process with the point measure E. I sample particle at the origin according to the law E, and I do one step of branching random walk with reproduction law Z, and the law after that step is unchanged. I recover the original, right? So it is a stationary point measure for the branching stationary distribution for the branching random walk. And they show that in the context of branching random motions, actually, you can look at this class of stationary point measures, and they show that those point measures, well, they will be shifted, decorated Poisson point process with exponential intensity, where the law of the shift S is anything you want. So they have no control on this shift, but they know that the law of the decoration is the limit of a branching random motion condition on making an unusually large displacement. So they don't identify the shift S, but they identify the distribution, the extremal point measure. So you see that the direct branching convolution equation characterizes the shift of the extremal point measure, and the reciprocal one characterizes the decoration, at least in branching Brownian motion settings. So we really hope that these kind of things should be true as well when dealing with branching random walks under some assumptions, which will be something like A1, A2, and some A3C, which asks you not to be in the regular or the boundary case, but outside of the boundary case. Okay. So yeah, sorry. Here, so what we expect to be more precise, so is that point measures which satisfies E is equal to Z convoluted with AI and to E convoluted with I should be represented as a decorated Poisson point process with exponential intensity, with a decoration D that only depends on the point measure Y, and a shift that depends only on the point measure Z, and a constant that remains unfixed. So you having both sides of the branching convolution equation would characterize the point measure E up to shift by a constant. Okay. So then I really cannot make this work. Sorry. Oh, thank you.
Thank you, Bastien, for this lovely talk. Are there some questions? Yes, I was puzzled at the beginning of your lecture when you said that when you have an infinitely ramified distribution, you can associate with it the branching Levy process, but you need an exponential moment condition. Okay.
Yeah.
So is it really necessary, this condition, or is it a technical point?
It's not necessary in the sense that I know some branching random walks that have no exponential integrability condition, but it's quite difficult to work with them. So it's partly due to the fact that I discussed a little bit before, right? That the branching convolution operation is not stable, is not continuous for the topology of vague convergence. So to replace this topology of vague convergence, we replace the point measure by the point measure with a Gerzanov term, which is e to the theta x. And so now you replace those point measure which has infinite mass by point measures that have finite mass but some weights. And we use then the weak convergence there, and using the weak convergence instead of the vague convergence allow us to control for particles that go far to the negative part and then give birth to something with due to some low probability event. And this, I don't know how to make it work if you don't have this exponential integrability condition.
Okay, thank you.
Thanks, Bastien. So if I followed you correctly, you're studying this equation because you have in mind the convergence of the rightmost particle towards something, it's the third order, right? So it's the first order of the rightmost particle, second order should be deterministic as well, and then the convergence in distribution. So I just wanted to know what you already know about the convergence of the process at the rightmost position, law of large number,
right,
fluctuations, and so on.
So actually, what we take interest is really this the convergence of this point measure, right? The position of all particles at the nth generation shifted by this constant m sub n. So it's already known that this converges in distribution for the topology of vague convergence to some shifted decorated Poisson point process with intensity the infinity e to the minus theta x, something like this. So this Mn is given by first order is v times n minus 3 over 2 theta log n, and obviously you can add any constant there, right? It's this, and I can add plus 3 or minus 2. So it's really no surprise that the limiting point measures that we obtain, we expect to be able to characterize them up to shift by a constant, right? So yeah, I just write it like this. So now what I'm saying is that to use the limiting decoration, what we have to focus on here is just this parameter v, right? This v times n, because then mn plus 1 is equal to mn plus v plus a little of 1. So this is what will replace the condition expectation of e to the theta z sum of the e to the theta zj finite by the sum of e to the theta j equal to 1 for application to the limiting point measure. Yeah, and here, so this logarithmic correction happens under some particular assumptions on the branching random walk. But you could imagine to degrade them, and instead of having asking for finite variance condition or things like this, maybe do something with less integrability conditions. Then you would have something that is not 3/2 log n, but maybe n to the 1/3 or log n, or maybe different things. Well, you could still use this decomposition to identify the limit, provided that you are sure that it converges. So it's quite a part that we were not able to work with. We cannot use this branching convolution equation under only the assumption of tightness of this family of variables. If we were able to say, okay, so I have this family of variables that have some branching property and that are tight, can I show that they have to converge to this family of shifted decorated Poisson point processes? So far, we don't know how to do. What are the right conditions to ask for this to apply?
So at the end, you presented a two-sided equation, yeah, with y and z. Maybe I misunderstood, but there must be some relation between y and z. Can you dwell on it?
So not necessarily. So it would be the same point measure. For example, if I were to look at a classical branching random walk, but if I were to be looking at a branching random walk with inhomogeneities in time. So for example, I could define a process that evolves according to a reproduction law, which is z up to time n/2, and then between time n/2 and n, I would reproduce according to a different point measure y. So this situation, it was introduced by Fong and Zaitouni, I think, and for example, Bovy and Hartung obtained very nice result of convergence of the extremal point measure in the context of branching Brownian motions. But what we would expect is that similar results hold for any branching random walk. And so the limiting point measure would satisfy this double condition. And equal to E convoluted with Y. Okay, up to some shift to make the speed equal to 0. But okay, so this double condition, and it would work for most type of point measures. And actually, with my student Mohamed Ali, we also Mohamed Ali Belloum, sorry, we also found another context where this type of equality occurs, and that's when you work with multi-type reducible branching random walks. So when you have two types of particles, and particles of type 1, particles of type 1 can give birth to particles of type 2, but not reciprocally. There are some contexts where particles of type 1 make more children than particles of type 2, but particles of type 2 move faster, where actually the extremal process after some long time look a lot like those time inhomogeneous branching processes.
Yeah, so we have a question from the chat by Zhenya Osun. So you considered the supercritical case, but is it possible to consider also the critical or subcritical case?
So yes and no. For what we did with Pascal, not really, because if you iterate the condition E equals Z equals Z equals Z equals Z equal E, well, with very high priority, Z equals Z equals Z equals Z will be empty. So you will no longer have particles, and then the only fixed point would be particles which have zero particles. But for this condition, where you have E convoluted with Y, there you can absolutely use subcritical branching lobes. You could have, for example, you could consider a branching random walk where everyone moves as a classical branching random walk up to time n-1, and then between time n-1 and n, everyone makes an exponential jump and see what happens. So then the second law would just be everyone make exactly one child, or everyone make one child with priority of half, for example. And this type of expression of the limiting distribution would still be correct. I mean, at least I expect.
Okay, are there any other questions, maybe? Oh, okay.
So can I actually unmute Andreas? Maybe that would be easiest. So let's try. So Andreas, can you unmute yourself?
Yeah, I think I've done it. Hi, Bastien.
Hello.
Thank you for the talk. So this is all very one-dimensional, and
yeah.
Of course the whole story is built to accommodate for the extremal particle and the decoration of mass around it, and going into a higher dimension poses a large number of problems, least of all conceptualizing what the analog of this story should look like. But we do know there are scenarios where you have a kind of a spherical growth. So your first order, you have it on the board, there's a first order linear order growth. You have logarithmic fluctuations around that, and then or a logarithmic correction, I should say. And now you're looking further into the decoration around that. So in the scenarios where you have spherical leading order spherical linear growth, what can you do something in higher dimension around this? And I really mean higher dimension, because of course you can project, you can ask for spherical symmetry and project everything onto one dimension, but I really mean higher dimension.
Yeah, so I think I agree with you in some sense. You can, if you are in higher dimension, you can still define the boundary of the process in some sense. You can look what happens near a border in some specific direction, then you just project to dimension 1. But you can, for example, look at the norm as well of the process. And if you look at the norm of the process, you have some nice properties that remain true. So if you imagine that you have your spherical process after some large time, so you have particles that are distributed around there, well, you would still be able to describe this the extremal point measure in these settings by saying, okay, so the extremal point measure should be shifted, decorated Poisson point process with intensity e to the minus theta x, which describes the distance for the topmost particles. E to the minus, well, okay, Cx for the position. I would have instead of a variable s that describes the shift due to what happened at the beginning of the process. I would have a s of theta or s of d theta, something that describes the shift in the process in the direction theta. Because if at the beginning of the process, my earliest particle moves by, let's say, 3 steps to the left, then the full rest of the process will be moved by 3 steps to the left. and I will always have more particle on the left than on the right of the process. So you would have a S of z theta, and you would have a decoration point measure as well. But this decoration point measure is exactly the one that you would expect in dimension 1. Because, well, if I look in the neighborhood of this particle and let particles live for a small time, well, the only displacement that will matter is the displacement in the direction of this large particle. The orthogonal displacement does not move much the norm of the position of the particle. So I would expect something similar to what we did here to be able to work. So, okay, we would have to replace the result we obtained with Pascal to accommodate for the angles, but for the result of Shinchin and Christophe and okay, and I don't remember Shekal's first name, but you see my point, right? For the second part, you would still be one-dimensional in some sense.
Okay, just maybe you know this paper. Go and dig it out. I'll send you the reference otherwise. Biggins wrote a long time ago about an asymptotic convex hull, and it wasn't always spherical. But I guess this is...
Yeah, so here it would be for BBM, right, where you have spherical invariance. So if you were looking to branching random walks, you would have an ellipse, I agree, I mean a convex shape, but you can still look at the position of the particle related to that shape, right? So something that is position of the particle minus something that depends on that shape, plus a log term, and then fluctuations of order 1. I think this kind of description should still work in these settings.
Okay, anyway, thank you very much. Thanks.
Okay, so I suggest we thank Bastien once more. Thank
you very much.
And we're going to continue with Maria Vares, and we're going to try to now move to the remote speaker setting. Okay, we can see you now.
Hi.
Hi.
Can you see my screen?
Yeah, we can see you. Il faut que tu la mettes en...
Can you see my screen?
Tu la prennes et que tu la mettes en highlight.
Alors, oui, elle doit être tout en haut, mais c'est bon ça.
Non, il faut que tu la highlight.
Can you see my screen?
Yeah. Yes, we can see your slides. Yes, exactly. And,
Okay.
and now we can see, well, at least in Zoom, we can see both you and the slides. Here we can see only the slides now.
Okay.
So we're going to see there's a way of seeing both. Just give us a minute. Il faut enlever le partage d'écran.
Je pense que tu peux lui dire de remettre ses slides. Parce que
Are you still sharing your slides, Emilia?
Yes.
Okay, so we did some.
I see them because I have, yeah.
Okay, we did something wrong.
Hmm?
We did something wrong here.
Yeah, because instead of my slides, I see my face.
Can you try to share again your slides? Sorry.
Okay, yeah, sure.
Wow. Okay, so at least we're seeing the slides. Nope. Moi, j'ai juste mode côte à côte.
Mode côte à côte. Ah, that's good.
C'est ici.
Intervenant. Et voilà, super.
I think we're almost there. Non, là c'est trop. 100%.
Ouais.
Ok, let's do that. Bon. Ça va comme ça?
Ça va bien. Hein.
Okay. All right, so we're now ready. And our second speaker for this afternoon session is Maria Vares.
So thank you very much. I really thank the organizers for giving me this opportunity to send my best wishes to Jean and this special occasion, participating in this meeting, and now as a way also to thank him for his very important collaboration with Latin American probability. Yes, of course, in Mexico, but also in other countries. And well, I would like that my little excursion wouldn't be from this in this way, you know, but I am in the epicenter of these pandemics, so I have to stick here. And what I'm going to talk is based on joint works with Luis Renato Fontes from São Paulo, Domingos Marchetti also from São Paulo, Tom Manford from Lausanne, and Daniel Ungaretti, who is now in São Paulo too. And at the end, I will touch a little bit some ongoing work with Marcelo Hilario, Daniel Ungaretti, and Daniel Valezin from Holland. I think he's in Holland still. So let me start by the very classical contact process. So you have a graph, locally defined. I mean, very soon I will stick to ZD, and you have a Markov process on the 0-1 configurations on the vertices of your graph, which 1 means that individual at X is infected at time t, and 0 means that the individual is healthy at time t. You can have this interpretation. So an infected individual transmits the infection with a given rate, which is the parameter of your model, to each of its healthy neighbors, and it gets cured with rate 1. These are the things which can happen. So you identify your process with those, the subset of the vertices which are 1, which are the infected individuals at time t. So this is a very classical process, which was introduced by Harris back in '74. And well, there is an important interpretation. That's the one we want to give attention, which is based on the graphical construction, which is called Harris graph. So you think on the space here is your graph, and then there is a time, and you think of this percolation substructure, which is the following. For each edge, you think of Poisson point process in both directions of the edge, which have rate lambda, and these are the transmissions. And on each vertex, the line on the top of each vertex, you think of cuts, which are simply the Poisson point processes rate 1, which refers to the cures. No? So your process is taught as a D+1 percolation system, in just this +1 is continuous, and constructed through paths, where the paths move in space according to the arrows, and they are not allowed to cross any of these crosses. So this is a very classical object. And it has an important thing, which is of course well known. There is a dynamical phase transition with a quite general setup, critical parameter lambda, which is positive and finite, such that if lambda is less than this lambda critical, then the infection is extinct with probability 1. And if lambda is larger than lambda critical, then starting from a single infected individual, then there is a positive probability of remaining forever. So there is a endemic situation. And so that's classical, but in some situations, like more general graphs, like trees or other situations, this supercritical regime can be split in two pieces. Like if there is an interval where you might have survival, but the infection doesn't come back to where it started. Say, suppose it starts at the origin, it doesn't come back infinitely many times. And on the other hand, if lambda is large enough, you do have so-called strong survival. So that means that the origin will be infected for arbitrarily large times with positive probability. So in the ZD scenario, these two things coincide, lambda 1 and equal to lambda 2. So you have only two situations. And if lambda is larger than the lambda critical, there are two extremal invariant measures, and the process will converge to a mixture of these two. There is a huge literature on this process, including in the books of Tom Liggett. So what we have looked is that we call the renewal contact process, because we want simply to consider the same percolation structure, but replacing this point process of the cures of recovery and also the transmissions by more general point process. So it's somehow also in the spirit of contact process in random environments, but it's not the same. So you have the same diagram, the same graph. The only difference is that the cures are given by a different type of point process or the infections, the transmissions. And the question is the same because your process is constructed as paths. So you want to know if there is percolation or survival. Survival just means that I will starting from a finite set, then there is a positive probability of having infinite paths. So that's the question we consider and brought us to this process. Well, I mean, I will say a little bit about the motivation for that, but that comes naturally if you see, for instance, a natural question that's, in fact, which was our basic motivation is, for which measures do we have that there is survival, no matter how small is your lambda? That we were motivated by that, by looking at, by thinking of some one-dimensional percolation, long-range percolation, and then would like to know if adding a small lambda in the other direction, we would still have percolation. That was our original motivation. So the question is, which measures, starting, say, from a single infected individual, then the probability that the infection will stay forever. I mean, there is a positive probability of infinite paths. It's positive for all lambda. No? That was the question. Okay, and the monotonicity in lambda that we are going to consider. I mean, sorry. The example that I'm going to fix will be that in the cures I will keep I will put a more general process, and in the transmissions I will keep the Poisson. So the Markovian property is already lost because of this more general renewal process on the cures, but there are some properties that are preserved, and one of them is the monotonicity in lambda. Sorry, because I missed one slide here due to my mouse, and so that's the example that I'm going to consider first. So our graph is ZD. The transmissions are given by Poisson process, and the cures are more general renewal process. So the Markovian property is lost. Some other features might be lost as well, which are important in the study of the contact process, like some FKG property, but we are going to try to manage over that, okay? Sorry, I am... so the tools, basic tools of might come from, since we are looking at this particular example of renewals, might come from strong renewal theorems under some regularity on mu, but we would like to have less regularity on mu, and then we might need to deal with that, that not necessarily you do need a strong renewal theorem for the estimates that we might need, okay? So that's the first question we addressed. And in this direction, there were two theorems. The first is that, which you might immediately think of it, is that if your tails are heavy, your measure has heavy tails, then you would expect to get big gaps without cures, and then you would expect to have lambda critical equal to 0. That means survival for any value of lambda. So this would be the main ingredient, but of course, in order to prove things, you might need some extra regularity, and that's will come in the assumption. And well, here it's just a very vague information because it does not even imply strong survival, because it's simple to imagine that if the tail is fat, heavy enough, then you find a tunneling event, that you find a big gap, then you are able to communicate quickly to the next big gap, and so on and so on, and you get an infinite path. So that's kind of simple to see that this should be true. And of course, it's enough to consider one-dimensional because I'm talking about survival. So if I have survival in one dimension. But the same conditions that we put here for this theorem, that I will make precise in a minute, imply that you do have complete convergence. In the sense that no matter, take a fixed lambda positive, then starting from any initial configuration, then you do converge to a mixture. If it survives, it goes to the point mass at the configuration all 1. And if it dies, it goes to, of course, to the empty configuration. Here is the weak convergence, of course. So it tells that under assumption of survival, you expect to see a big block of ones. Okay, that's what you have in a general scenario with some quite general conditions with heavy tails. These assumptions for these theorems are more general, but they include, of course, the case that mu is in the domain of attraction of a stable alpha less than 1, but are more general. So let me just state those conditions. I have stated them as they appeared in the paper. Don't spend too much time on those things. The important thing is that they are much more general than stable, that they allow, for instance, to change from one power alpha to another power alpha prime along the tail. So these are kind of natural. The nuisance here that we have is this one, that we are not able to get rid of that. But anyway, you have a quite broad set of measures for which you can prove that. Of course, there is this border alpha equal 1, which is the important thing, but it's not addressed for the moment. Okay, so these are, and then you immediately ask yourself if you can say something more in this particular case. Okay, that's because for the complete convergence, you can do much more robust class of measures mu. But if you make this assumption of being in the domain of attraction of a stable, maybe you can say more. And two results that I would like to mention in this, one of them by Fontes, Luis Renato Fontes, Pablo Gomes, and Remy Sanchis, is they considered this class of measures for some values of alpha in a finite graph, and they are able to prove that there is a phase transition on the size of the graph. So there is a value of the V plus. If the number of vertices is bigger than that, then you do have positive probability of that the infection stays forever for any lambda. No, lambda is fixed, positive. Otherwise, if is strictly less than that, then you have 0. And there is one value for which this is not known. I imagine that they can extend these results also for smaller values, but maybe since they use the strong renewal in a heavy way, so maybe that was the reason they have considered this case. This is about the question of survival or extinction. About convergence, one can also say more under these conditions. And that's the following. Since we proved that under the conditions of theorem 1, we proved, I just mentioned, I didn't prove, but anyway, we proved that there is this complete convergence to the mixture of point mass at 1 and point mass at 0, then you'd expect that not far from where you are looking at, there will be some infected people. No? So you expect to be able to say something quite strong about the probability, given the renewals. So if you know the age, if you are looking at a set of vertex, and you know the age of your renewal process, so the time since the last mark of cure, you would expect that one of these neighbors, you have 2D neighbors, one of these neighbors maybe is infected and will infect your process. So you will expect to say very precise about the conditional probability of being at 1, given the renewals and given that you survive. So this is made precise in a theorem. I mean, this part is still a preprint, which says exactly that. I mean, if you are, but this is restricted to measures in the domain of attraction of a stable. So when you condition on the renewals and the survival, no, then you are able to prove that the conditional probability of being infected at time t is basically given by this. It's very close to this. What does it mean? That's exactly, you have 2D neighbors, and this is the age. So you expect that at this time there will be infected people on the neighborhood of your origin, and then this is just the probability that that one of them will, there will be an error from the Poisson process. So this, some sense, it tells you that you get something almost deterministic once you know the renewals and tal. And well, I mean, this is for alpha less than 1/2. So you need these regularity conditions for the strong renewal theorem, like in the paper of Caravena and Doni, and that's included in the assumption, but I don't enter into that now. And the case that alpha is less than a half, is bigger than a half, then this 2D is not okay. You need to change 2D by 2D minus K. But I just say that this result will not be okay, but you can improve by replacing 2D by something else smaller. Okay, so there is a way to go further in the regular case, but I mean, this is more delicate, so I don't know if one could be able to extend for the same conditions of theorem 1. I think it's more delicate because it involves really dealing with the strong renewal theorem. Well, but this is these results that I mentioned have to do with the question of getting extinct. And now you might in the same way ask, well, because you would like to know it's going to be extinct if and only if something, not for all lambdas. So, but so looking now from the other side, you want to say, when can we say that lambda critical is positive? So we gave some sufficient condition to have survival for all lambda, and now you ask the opposite. Well, there is an easy fact, this is completely easy, that if your measure has second moment, then this has to be positive for any dimension. For the simple reason that if your measure has a second moment, you look at any time t, that the lifetime of the renewal in that time is going to be integrable. So it's easy to see that you can compare your process. You can compare it with a sort of with a branching process by looking at the fact that the transmissions are Poisson. We are using here the transmissions are Poisson, and you can compare it with a branching process such that if lambda is small enough, then this is going to be subcritical, just basically 2D times the expected lifetime total, which is bounded by, in this case. So that's a simple thing, very general, but of course there is a huge gap between this and the condition we had on the other side. So you need to improve that. One thing that we did in order to improve that was to look at the case that the measure mu has a density and a decreasing failure rate. This assumption that looks, why did we put that? Well, the reason is that when you have a decreasing hazard rate, you can construct the renewal process of the cures as an increasing function of a Poisson point process on the plane. In this sense, and then this allows you to use FKG. I mean, this construction is of course very classical and simple. You imagine that you have your hazard rate function in a graph here. This is the time. This is the other dimension space here. And these points, instead of being drawing like this by hand, they were Poisson process. So you just have an algorithm to construct your process. You take the first, then you move your graph to this place and take the next one, which is below the graph of your function, and so on. And as you proceed in this way, if age, this you can do for any age, but if age is decreasing, this will give you an increasing function of the marks. It's easy to verify. And so since this is an increasing function of the Poisson point process, it will say that your process will have some FKG inequalities to use. That means increasing events. Increasing means in terms of the path, because that's the way you are looking, which in terms of marks means decreasing for the crosses and increasing for the arrows. So if you have increasing events, they have positive inequality. Now you have increasing events will satisfy this. If you have, so there is a path that goes here, there is a path that goes there, and so on, and you take the intersection, the probability of the intersection is going to be bigger or equal than the product of the probabilities. And this allows us to use some further tricks, which are not, which are sort of natural when you want to study percolation. And in this way, we were able to prove that in dimension 1, if mu has this decreasing failure rate and has a moment larger than 1, then lambda critical has to be positive. And the reason why this is restricted to dimension 1 is because our argument used crossing paths. We wanted to compare the probability of having a time crossing with very strange, maybe spatial crossings that could be two with a very small slope here. And well, after a certain number of them, you can cook the path. No, so if they are in one dimension, you can, out of that, you can construct one path that does what you want. So these are kind of arguments very similar to sort of those which are used for Russo-Seymour-Welsh estimates in percolation. But the main problem with this argument is not so much the density and the decrease in failure rate, which is shouldn't be essential, but which is understandable. That if you have attractiveness, you can do something more than in general. No? But the fact that it's restricted to one dimension, then it's and of course there is the border line, but that's a more delicate issue. So then after some efforts, and this is what we can prove. Finally, we can get some condition that works in any dimension, and that involves only moment. There is no attractiveness assumption here. So, and this is still also as a preprint. So we have the same setup. I mean that the cures are the ones which we have the renewals, the transmissions are the Poisson, no? And we have a mu which is a little bit more than the integral. But this one is in the domain of, allows domain of attraction of a stable 1. And under this moment condition, and it's a little bit delicate, so in the sense that our theta here cannot be arbitrarily small, depends on the dimension here, then we do have this positive lambda critical. So of course it remains the question, which we still are not able to answer, if the exact relation between positive lambda critical and finite first moment. Because in the same way that here we can see, we can prove, I'll give some sketch, no? That lambda critical has to be positive. That means there will be extinction if lambda is small enough. You can give examples. It's not hard to give examples in one dimension of distributions in the domain of attraction of a stable 1 for which lambda critical is 0. But at least all the examples we have, the first moment is infinite. So the first question that we started with, which was motivated by the tail 1 over t, or say the tail constant by t, still remains open to us. We don't know how to deal with that. That's, but you know, here of course there isn't, it's optimal for our argument, but one expects to be able to get better than this, of course. But if one is able to prove that finite first moment suffices, that's another story. And that's the open question that it would be interesting to answer. Okay. So maybe I am a little bit with this mouse here. No, sorry. I mentioned that there is some ongoing work with this more recent with Marcelo Hilario, Ungaretti, and Daniel Varesin, and that's in this work now we have consider a much more general class of point processes. So in the sense that you can deal with renewals in both process, both point process, the transmissions and the cures. But our mode is still we stay within the independent case. That means that there is independence from one edge to the next edge, you know, and one vertex to another vertex. But there is an indication that we have a method that can deal with more general random environments. But so let me just use it as an occasion to mention one of the simplest result in this direction, which is connected with a recent paper by Linker and Hemenick. They considered a dynamic environment on the edges. In this, what does it mean? Well, the edge process changing, so the edges might get activated or deactivated as the time goes. Okay, I apologize that there is some work going on my street, and I had to opt between the risk of having this noise and weaker connection on the internet. So I'm sorry, I think they started noise right now. So in this paper by Linker and Hemenick, that they consider dynamic environment for the edges. So the edges might be open or closed, and this configuration changes over the time. And given the edges, they have a classical contact process that the transmissions can happen only through the open edges. So in short, there are two parameters, a P, which is the probability of the edge being open, and there is a V, which is the rate at which things change. So an edge that's closed, it opens at a rate V times P, and if it's open, it closes at a rate V times 1 minus P. So you simply think of the usual dynamic bond percolation on ZD that has a parameter P. That means you update your edges, as has been studied a lot, but you put a rate V, so just rescale the time by V. No? So given the edge that you have at time t, your process at t evolves like a contact process. So if it is infected, it might be cured at the rate 1, and if it is healthy, it might get infected with a rate which is depending on the number of neighbors which are infected and have an active edge between them. Okay, so in this paper, they proved various results about this process. Of course, if your V is going to infinity, that means you are averaging your environment, then you expect to have that lambda critical would converge to something. But when V goes to 0, this is more tricky, and that's the case we want to look at. So they proved various results. Some of them were very general in the more general graphs, but this one, what happens when you make V go to 0, their argument is very much one dimension. So they are considering Z. So, and the result is, I mean, that's what you would expect. What can you say? The first thing, what can you say about the critical value? That means the infimum of all the lambdas such that there is a positive probability that you stay, that the infection stays forever. That's the same question. And you want to know what happens with this lambda critical as V goes to 0. Now, so if P is less than P critical, and if V were 0, then lambda critical would be infinite because you don't have an infinite cluster, so your contact process dies out. So because the environment wouldn't change, but the environment is changing. So you have you are in a cluster. Maybe before the contact process dies out, you are able to find a link to, because a new cluster appeared, because there's some links opened, and you are able to go to somewhere else, and so on and so on. So, but you want to know what happens as V goes to 0, and you can prove that for any P less than P critical, then this lambda critical goes to infinite as V goes to 0. It's not a big surprise, but it's not, well, I mean, it's more, it requires renormalization argument, at least the way we can do. But it's an application. You can think of this as a renewal contact process, but the renewals now wouldn't be in the cure marks, but in the transmissions marks. The cures would be 1 exponential Poisson. You can think of that, though it's not necessarily the most convenient way, but that's what in fact motivated us to look at the renewal contact process in both processes, both Poisson process. And if P is larger than P critical, then you should have this finite, and this should be kind of uniform, and that's a different argument, and that's simpler as well. Okay, so let me give you a little bit of an idea of the proofs. What are the ingredients? Well, so for these results on survival, the main thing is that you need a lower bound on the probability of a big gap. No? So, and lower bound like that, the probability that you have a gap, I mean, you can find an epsilon, that there is a t to the epsilon gap. You have some uniform estimate for a large t. This is can be proven under the conditions that I stated in the beginning. That means beyond the domain of the strong renewal theorem. And using this, you somehow can prove that with very large probability and not very far from the origin, say in a distance which is of the order logarithm, you find someone that is infected and stays infected for a big proportion of the time. So stays infected for a time of order t. So that will be the main ingredient for proving the complete convergence. And also when you combine this with the strong renewal, you can prove that more delicate result on condition on the renewals that I mentioned before. So these are the two ingredients. I mean, there is some work to prove this, but that was in the first paper that I mentioned. And for the other ones, that's the one I want to tell a little bit, which are the main ingredients, is for the second theorem. No? So the classical ingredient is simpler in some sense, because now you are in the situation that you have, it's integrable. It's a little bit more than integrable. No? So we need some f with a certain, that grows in a certain way. So If it's interval, you always can find an f, which is non-decreasing, goes to infinity, in fact, and this is fine. That's of course. But we'll need some control on the probability. But well, if you have an interval, then this is just by using the classical renewal theorem, because you are in the context of inter-arrival distributions. So with this basic tool here, just tell some uniform estimate, a uniform estimate from above now that you want on a gap, of having a gap, no, that means not having a Q mark. You would like to be able to show that if lambda is small enough, then your process will get extinct. And so that's the main point that we, our last, the effort in the last times for this thing. Well, you would like, so it's a question of percolation. You want to show that if lambda is small enough, it doesn't percolate. You don't have infinite paths. No? So you take a box, a space-time box. So we took here 2 to the n in the space, and in time some bn that has to be chosen. And we want to get a bound from above on the probability of having a crossing. No? Crossing could be in space or in time. That's the thing you want to prove. You want to prove that if lambda is small enough, then the probability of having these crosses vanishes in the limit as n goes to infinity. Okay, so the 4 basic events that we need to consider, maybe 2 would be space, time, and space. But in order to make a renormalization, we need to work a little bit. So we need to split these things. So there will be spatial. That means just you go from one side of your box to another one in space within this time. That's what we call partial crossing of the box. Time crossing, that's obvious. And it will be convenient to consider half crossings. So here is space half crossings as well as time half crossings. That's just, these two, they come because of the argument. And of course, what you want to prove is that the probability of surviving forever goes to 0. So of course, whatever is lambda, you bound the probability of surviving forever, starting, say, from the origin, doesn't matter, by the, well, if it has to survive forever, it has to exit the box. So it can exit from the top by a time crossing or from one of the sides. No? So you have 2D of these half crosses that you can do. It doesn't matter if it's here, it doesn't matter too much if you consider half or box. That's so you want to prove that these probabilities go to 0 as n goes to infinity in a way that the point is that there are the renewals. So, and you have to condition on where they start, no? Because you don't have independence anymore, no? in the time direction. In the space direction, it's still simple because it's independent. You know, we have this Poisson process, so they are independent. So you need to bound these things in a uniform way, and this uniformity has to be achieved when you shift your boxes in space and time, and when you consider renewals with the inter-arrival fixed, now of course mu, but they start at different time points. Not everybody in the box has to start at the same time. No, just that is below 0, say, or below t here. So you need to make an estimate of those probabilities of the 4 events that I mentioned before in a uniform manner with respect to these starting renewal processes and as you shift. That's what you want to make. So you want to devise renormalization scheme that shows that they have to go to 0 if lambda is small enough. So of course, there are some obvious relation between these four quantities that time crossing is the probability of a time cross is less or equal than a half time crossing, of course. A space is less or equal than half space crossing. That's trivial. And in fact, in this space, you have a spatial crossing is less or equal than 2 independent spatial crossings. That's obvious because we are taking in this context, we are taking the transmissions as independent Poisson process. So these are immediate relations, and we need to find a way to estimate recursive these things. So for the time, so remember we have these boxes which are base is 2 to the n, and in time is bn. I don't know exactly how I'm going to choose bn for the moment, but I want bn to be large enough in this with respect to bn minus 1 to be at least 6 bn minus 1. At the end, we will need much more. But anyway, why? The idea is simple. No, you want to know, you want to make a recursion that if you have a crossing at scale n, there should be 2 crossings independent of scale n minus 1. And then you get a recursion, then you just go to the first scale for which this happens, and then you need to make lambda small enough such that the probability of this at this fixed scale is not too big. No? So the idea is simple. So you take this Bn in this way, so this half crossing will offer you 3 boxes. No? And what you do, well, suppose you have that in the middle, you do have a cure everywhere. So there are 2n d, 2 to the dn verses. And everyone gets a cured. So this separates the box, this upper third here and from this one, simply because there is a renewal. So you have an independency. So there are the possibilities that you do have that. If it doesn't happen, well, there is this probability that it doesn't happen. One of them didn't renew. And if it happens, you do have these independent boxes. So there are 2 of these boxes. But observe that these boxes are not the n minus 1 box, because in space, you have something larger. No, the scale n minus 1 boxes would be 2n minus 1 here. But of course, by looking at the geometry and with some entropic factor, you compare these with the scale n minus 1, because or there is a space crossing or a time crossing. But you need to but it's just a matter of thinking of these boxes here and splitting them into 4 pieces along each of these coordinates and examining the various possibilities, and you get that the probability of making a crossing here, this time crossing here, is bounded by what is inside this parenthesis. There is these entropic factors here. I mean, it's just a union thing that will happen. So you can bound the temporal crossing at scale n by 2 of scale n minus 1 that will involve both temporal and space. And for space, you can do the same. It is somehow simpler in the sense that the space is already independent when you move different boxes. No, they are independent, but they use this entropic factor here, and you can do something similar by a similar analysis, just that it doesn't involve, you don't need to pay anything. You don't need to pay because they are independent. So that's the usual decoupling thing that you want to do. You just pay a price here for the due to the to the where now you have a crossing of scale n, and you will find within these boxes cross of scale n minus 1. But where you are going to find it's not so clear, so you have to pay a little bit, because where you are going to find in your boxes. There are all these scale n minus 1 in the time boxes inside. And the square is just because we had to. There will be two. So these are the basic ingredients. That's where most of the effort, I mean, you have to, I mean, it took effort to realize that it could be done. But once you have these estimates, then it's a matter of making, the computation. No? So you need to control both, so you simply sum both of them, and you want to, from what we just mentioned in the two lemmas, you had a recursion like that, and now you need to control both. So you need this guy and this one. No? So you need to have both of them under control. This has to decrease, so f of bn minus 1 has to grow enough, and this one also cannot grow too much, has to decrease. So you need to control both of them. Okay. So the goal is, you like to prove, to find the df such that after certain starting from certain scale, if at the scale n you have this exponential decay, then also at scale n plus 1 you have the same exponential decay. That's your goal, not to have that. So you need to examine this recursion here and cook up something that works. And something that works if you take f, which is the one that appears in the condition. So e to the theta logarithm square root with a certain theta. And bn will grow like e to the n squared. Then but you note that the theta is in the denominator here of this exponent. So that's why we need theta to be large, because it cannot be too large this, because this will spoil everything. So by putting this and assuming that you have your theta as we wanted, that means we need to stick in some alpha between these two numbers, and that gives you the condition that we had there, that theta has to be larger than something. This works. I mean, in the sense that this works. And if that works, that's okay. You just need to prove for a given scale, and that's simple, because you just make lambda small such that the probability of having a crossing of these finite boxes of a given scale goes to 0, and that's where then this becomes simple. So so as you see, these conditions that we get there in this theorem, they reflect our construction, and they are of course not optimal, but we don't know the optimal ones for the moment. One question that appears naturally, and that's something that spoils, that that's something that creates a difficulty, and we would like very much to be able to say something in order to use it, is if you have two interarrival distributions and you would like to put one of the renewal process inside the other, now to couple, such that this renewal is contained in this point process contained in that one. Of course, there are some obvious cases where you can do it. And it's easy also to do if you have a decreasing hazard rate for one of the measures. Then it's also easy using that classical coupling. But in general, I mean, we don't know how one could explore this kind of thing. And there is a very important, I think, it's a classical result by Hermann Rost, which was published long ago. I don't remember exactly now the year, in Invenzioni, where he exactly says, this happens if and only if, I mean, that the knee can be written as a sum for a certain randomized stopping time of independent realizations of the mu. This happens if and only if some condition that involves simply the renewal measures. I mean, that you can compare you make the convolution of the renewal measure with the other measure, that this is comparable as measures. So this, we were very enthusiastic when we saw that maybe one can use, but we were not able to use it at all. In fact, I mean, in order to get inspiration how one could use, I went to see all the papers that used that cited that article of Herman, and there is, I mean, there is one by Jean, and but then I see that that's a completely different use. You know, that's something more theoretical, but we couldn't use. And so with that, I think I thank you, and happy birthday to Jean. And here he is doing some alpinism, not only mathematics, but alpinism. And after this effort, he had this nice view of Rio de Janeiro in the times that we were in better shape here in this country. So thanks a lot.
Thank you. Do we have some questions?
In the chat?
Certain of your results did not depend at all on the dimension B. Do you, and some other did, but do you expect the one who do not to hold for more general graph? I mean, provided that there is some growth condition for the balls, or say that the degree remains bounded, or?
Yeah, for sure. Yeah, I think so. Yeah, many things could be more general. Yeah, but you know, the basic thing, which is somehow the simplest in two dimension. No, in dimension one, two because it's space-time, and if finite moment is enough, I don't know. In one, d equal 1, that I don't know, and that's but I mean some results. But we are, you know, in all the situations we have already extended for some case where there is interaction, but not so much. But for renewal process on both, and but we are always not getting the border. No, that's the problem.
So, okay, maybe I'll first take the question in the chat that you can read here. So by Bruno. So maybe I can read it for everyone because it's written quite small. So in the contact process in random environment with subcritical P, do you know if lambda C is finite, or do you expect it?
With you mean in the fixed? With the fixed for any V? No, this one this one should be uniform in V. Because there is something which is simple. I mean, as there is not a monotonicity in V, but lambda critical divided by V decreases in V. It's not increasing. So as V goes to infinite, there is no problem. I don't know if I got you were talking about, the question was about this dynamic environment or more general environment? This result should be quite general, but
Je peux?
this one, I don't know. I mean, we proved in ZD, but imagine that can be. At P critical, I don't dare to make a conjecture now because we are still working. This is already proven, but at P critical. I don't know if that was the question. What happens at P critical?
Bonjour, vous m'entendez? Il y a le son là? Oui. Alors, je suis français, j'ai suivi les cours de Serge Haroche à Normal Sup Ulm. Voilà, peut-on reprendre les travaux de Serge Haroche dans une optique lacanienne?
Yeah, I don't know if you got that.
No, I didn't get exactly what was the comment or the question. For some reason, my chat here disappeared. I am not able to see it. If it's written, you have to read for me.
Well, I mean, maybe we can discuss this after the end of the conference. Are there any other questions? If not, I suppose that we thank the speaker again. So now we have a half an hour break, and we start again at past with the third configuration of the day.
dans ta poche ou sur ta ceinture, comme tu veux. Ça devrait marcher. Ça marche?
Ça devrait se débloquer, ça. Parce qu'il y a déjà pas mal de choses dans mes poches.
Alors, attends. Et
non, ne me foutez pas la merde. Hein. Tout marche là. Alors, Nicolas.
ça marche le setup ou pas?
Je pense, oui. Si ça ne marche pas.
Pas de retour.
Biparental, généalogie. Voilà. Chez maintenant, on ne sait jamais. Hein. Il vaut mieux préciser.
D'accord. Bon, d'accord, ok.
Dedans? Non, ça c'est celui d'avant. On a fait mis à tomber. Mais après, il y a tout un bord. Il n'y a que lui comme contact. Il répond. Il répond pas. Il n'a pas répondu. Ça pose un peu un souci. Mais il sait qu'ils avaient une liste de 30 pages. Et nous, ça ne rentrait pas. Alors, est-ce qu'on est bon? Ouais.
Ah non. Comment ça marche? Normalement, il devrait voir.
Maurice?
Il y a mon iPad. Non, je ne veux pas. Oui. C'est bien, c'est ce que je veux. Oui.
Okay, so welcome for the last talk of the day. And Yves Lejean is going to talk about, so the title, I'm not sure of the title, it talks about généalogie biparentale.
Biparental, généalogie. Oui, ça fait longtemps que je connais Jean, tellement longtemps que je ne me souviens plus très bien. Donc, je ne vais pas en parler beaucoup, juste un petit code pour ceux que ça intéresse, enfin, l'époque. 4656, third floor. So, good old days. So, when we worked actually together at that time. The first paper, as far as I remember, we did together was about score-rod problem, but I completely forgot the circumstances, and the result was probably the score-rod. But I really don't remember. anything about that paper. The second paper we wrote, as I remember, is with Jean-François Le Gall, and it was about super processes, which is an extended development about branching processes, as you know, which have been a lot has been said. So branching processing about population, originally population is increasing roughly exponentially or decreasing. So it's a situation in which is fairly dramatic, in which you have the choice between explosion and extinction. So I thought recently I've been interested with Camille Coron. We think probably is here for damage control. Yes, okay. So in a model of population which is more sustainable, where the population is constant. So this model is the size of the population is constant. People die and get born, but it's constant in size. So we did some contribution. I'm going to try to show you. Let's see first. Yes, I've been told that I should not go too fast. So this is not a time limit; it's a speed limit. And okay. So biparental genealogy. So what is the story? So what is the story? So the story. So let me tell the story roughly. So you can, of course, it's a mathematical model, so you can present it in an infinite number of possible stories, of possible tales. So the tale will be for today that don't look at the slides. Listen to what I say, please. And so you have a large number of coconut trees. On each coconut tree, there is a monkey. And at each time set, maybe every day, say, two monkeys mate, and they produce in some way a child. The child shakes a coconut, a random coconut, but not the coconut of his parents, by the way. It doesn't make much difference, by the way. Then the monkey who is in that coconut tree falls, eventually dies, and the child goes up this coconut tree. So you see you have a population of constant size. It is not, so this is a development of so-called the Moran model. So yes, what should I say? Well, I think that's fairly clear, but yes, so if you want to, so you can somewhat, is it readable? No? That's problematic. Maybe we should switch off the light because I have nothing else than that. Okay. What can I do?
May I make a contribution from far away?
I cannot zoom.
When you turn off the video.
So you have at each time step n, 3 different sites are chosen randomly. Kappa n, which is the site where there will be the killed monkey, mu n and pi n, which are the parents. So we don't consider the sex in this story. So the monkey, les singes et les guenons, pas de différence. And you choose the parents, and they produce a child who kills the occupant of the site kappa n. And all steps are supposed to be independent. So the choices are independent. So I can show you what you produce with that. You produce a genealogical graph. So can you see this graph? Well, I think you can see, no? Oh, no, not much. This is a graph in which you see there are some oblique lines which denote parents, and some vertical lines. When nothing happens, you have a vertical line. So there are two possibilities. Either you have something like that, and then here he dies, or the parents survive. So you see, you get a graph in this way. Okay, so so this is the situation. So what is the issue? The issue is what is the genealogy, and especially some of the monkeys will be eternal in the sense that they will have an eternal descent. And you have to explain what happens, roughly speaking. So the first idea you may have, just to get a kind of general idea of what happens, is just look backwards in time, and you can look at the number of ancestors of a given individual. So you take an individual at time 0, you take an individual at time 0, and you look at its ancestry. So at the beginning, there is a large chance that you will have a tree, but since there is a limitation in size, after a while, you see that there will be some, the tree will not be a tree anymore. And so if you look at the number of ancestors at a given time, you have a birth and death process. So birth and death process that actually you can analyze quite in detail. Well, I will not describe that too much, but so what is the result? The result is that the birth and death process, the expectation, so you can, let me call it Zn. So as n goes to infinity, Zn, so the expectation of Zn is capital N over 2. So half of the total population. And actually, if you look at the distribution of Zn, you see that the variance of Zn is of the order, the Zn over n is of the order of 1 over 8n. So that, in fact, the proportion concentrates as n goes to infinity on 1/2. So to summarize, what you see is that in a large population, if you look deep in the past, each individual has approximately 50% chance to be an ancestor. Yes, but okay. So in a large population, but I'm just saying what is, in a large population, deep in the past, each individual has approximately 50% chance to be an ancestor. So, okay, so this is gives you this idea that there is 50% just by this simple analysis of the birth and death process. Now we want to be actually to do something which is more precise, and so instead of looking in the past, we look in the future. So first thing is to define what we can call the genealogical flow. So what is a genealogical flow? It's you define it, but let's say the idea is very simple. So you look at, so the ancestors now are at time 0, and this is fixed. So these are the ancestors. And then you look forward in time, and you see an individual, it doesn't matter which, at time n. And you build a genealogical tree. So it will not be a tree, but okay, it will be, for example, you can have things like that. So this tree will end up on certain ancestors, and each ancestor will have a weight, which will be the share of ancestry he has. It comes from the fact that when you have an ancestor, an intermediate ancestor, say, you look at his parents, they take half of the share of the ancestry. You could talk about genetic, well, okay, but basically it's just that you divide in two. So you can define this, you can write this in this form as a product of matrices. The matrices are random, and they are defined by these sites, kappa, mu, pi, kappa being the site of the killed individual, and mu and pi being the parents. So it's a very simple transition matrix, which is random. You multiply them in backward order, and you know that this is a flow, and that and you have all the properties of product of independent maps. So just to explain a little more, but I hope it is visible. This is an example of a genealogical tree. So you start with the individual I in generation 4, and you go up till generation 0. And eventually you see the weights each time is divided. So you have 1/2 on each side. You end up with 3 ancestors at time 0, one with weight 1/4, and the 2 other ones with weights 3/8, just by dividing the weight each time in 2. So as you see, it's not a tree, but so it's an oriented graph, which is a subgraph of the genealogical graph. So the total genealogical graph gives you all these particular graphs. Oh, all right. So now, so AN of IJ, I recall, was the share of ancestor J in let's say the genome of I, you see. And so you can sum on all individuals I of the population at time n, and it gives you the weight of ancestor J in the total population at time n. So it's really how much he contributed to the future. And this is a martingale, so people who are used to work with flows or with product of random matrices know that it is an obvious fact. This is Mn is a martingale, that's why denoted by M. And this is most obvious. So when you divide Mn by the total population, you have the share of this ancestor J, which I denote J0 to indicate the generation by 0. So this is the share of J0 in the ancestry of the total population living at time n. So there are a few results which are almost straightforward. The first is that Mn is a martingale for all j. Mn of j is a martingale. So it's a martingale which is bounded by n. So it's converging. It's positive. When you sum all the Mn of j, of course, you have the total size of the population, capital N. And also, which is a bit less obvious, which will not always be the case, but often, and in that case, it's not difficult to see, is in fact, this weight of an ancestor in the general population is also the weight he has on any member of this population. So if you take a specific individual I from the population at time n, and all these individuals actually have the same ancestors, the same distribution of ancestors. This distribution is, of course, random, but it is the same for all individuals. So, in fact, you are left with studying the martingale Mn. So what we want to know is what is the distribution of the various Mn of j, their joint distribution. So you know that they are not independent because when you let j vary, when you change the ancestor. But they are not independent because their sum is constant. So what happens? So to see what happens, we can do some simulation and hoping that your pseudo random number is not, we are not unlucky with it, you will get to suggest something. So okay. So what do? You take your martingale, Mn, you look at its limit. So for a population of size 100, you see, so here what I'm showing you is not Mn of j, because if I show you Mn of j with j from 1 to 100, you see nothing. What I'm showing you is order statistics. If you look at the order statistics, you see something. You see that the order statistics, of course, if you look at 100, it will be a different shape. It will be a different, I mean, what you see in blue will not be the same. It varies. Because what we get is so-called, if I want to be pedantic, it's an SRB measure. It's a random measure. So each time you sample it, you see something different. But you see something different, but not so different. Namely, you see that there is a general shape which appears. And this general shape, to discover it, you just push n, for example, to 10,000, in which what you get is not random, almost not random, and you see a shape, clear. So there is a phenomenon that we want to describe. Is that clear? Despite the invisibility of my slide, I'm sorry. But it's visible on my iPad, so it will be visible on Zoom for those who are not here. So, what is the result? So the result gives you what is the shape. So the shape of this, let's say, you see, this is the order statistics. So you look at some point which is integral part of nu with u between 0 and 1. So you are looking at some point on the curve And this gives you the formula. So you see that for u, if you remember what you had, there was, if you remember a little bit the plot, you see that it's 0 up to 1/2. And then suddenly it grows. So this is because half of the population has no descent, no infinite descent. But half has. But some among those who have an infinite descent, there are some who have more descent than the others. So this gives you the statistics of this more or less. So this is the shape of this is the equation of the curve. So this is one result. The second result gives you a result about the distribution of the weights of L being any number, but a fixed number, ancestors. And it tells you that actually this convergent distribution towards yes. Where normalization? No, I don't think there is a normalization. Here, Mn. So when you divide by n, oh, well, no, there is an asymptote, you see. But typically, the size is not so big. Typically, it's not so big. You can look again at the plot. Oh, what time is it? Oh, I have time. So you see the numbers are like 4, 6. Then when you look at the L ancestors, in fact, their weights are independent asymptotically. Of course, if you took all the ancestors, it would not be the case. So then you can define their limit distribution, and they are like L independent random variable with this distribution. Here you see it's a distribution which is a mixture of a delta measure, 1/2 delta 0, because there is half of the ancestor who have no descent, and then an exponential distribution. And the formula which is here is just the inverse of this one. So it's a relation which is, so the relation from B to A is fairly obvious. So we are left with proving B, in fact. So let me just give you first a hint why B is true. It's a sketch. It's not really a proof. It's a sketch. So how do you guess? Can you guess this result? How can you guess the formula? So to guess the result, you can assume that actually for large capital N, for large populations, these are in fact independent. And then the weights are independent. And then you look in one step what happens, and you take the Laplace transform of the weights. So the weights M infinity of J, in fact, the Laplace transform does not depend on J. It doesn't depend on the ancestor. There is a symmetry in the problem, which makes that it clearly does not depend on J. So looking at what happens in one step, assuming that you have an independence that you don't have, you end up with an equation for your Laplace transform. H of lambda equal 1/3 plus 2/3 H of lambda over 2 times H of lambda. And this, there is a 1/3 because you see, and a 2/3 because there is 1/3 of chance when something happens to an individual, there is 1/3 of chance that it is killed and 2/3 that he is a parent. And if he's a parent, he survives both by himself and by his descent. That's why you have the product h of lambda over 2. So when you have this equation, après un moment de consternation, well, in fact, you find that there is an easy solution, which is obtained by a homographic function, lambda plus 1 over 2 lambda plus 1. And this is a Laplace transform of the distribution I mentioned in the previous slide. So the distribution which gives you the distribution of m infinity of the weight. So if we were a physicist, that's it. You see, we have a good simulation, we have the formula, and we have a kind of argument which justifies the formula. So you could leave. So I still have 20 minutes to go. So let's try to see. So we are trying to find a proof, and so here is a proof. There might be other proofs. This is one proof. So we prove B. So B, I remind you, it's a distribution, the asymptotic distribution, and the independence. So the asymptotic independence. So we prove it by a moment method. So we look at the moment of powers of m infinity of 1, m infinity of 2, m infinity of L. So the weights of each of the ancestors to a certain power. And then if we believe the result of the theorem, we have a formula for this limit. So this is what we have to show. See, this is the limit product of 2 ki minus 1 ki factorial, where ki has a power of m infinity of I. So what is m infinity of n? You see, as depending on the ancestor, it's a random probability on your set of ancestors 1 to n. So what we are trying to get here actually is a formula for the moment of this random probability. So one way to interpret these moments, so let's say I denote it, if you want to denote it a little bit abstractly, you write this as a measure, which you can write nu and k. This is now a measure not on the set of ancestors, but on the set of k-tuple of ancestors. So it's on the set 1 to n to the power k. And so this you can write as the expected value of the tensor product, the case tensor product of the measures m infinity divided by n to the k. So this you can do actually for any flow. So what does this represent really? This actually is an invariant measure. The invariant measure, this is a general wisdom when you study flows. You just, okay, you have a random flow of, this is what I denoted by AN, the genealogical flow. And then you sample it by K random walks who move on the genealogical graph independently. That's a picture you have in mind to make sense of this horrible formulas, expectation of tensor product of K random measures. So you can think of these K random walks moving independently, but then you can average on the environment, you see, and then you have a random walk which is not K random walks working independently. You see, then you have actually K points interacting in some sense through the random environment. And this gives you a random walk now on the product set, and the measure, this measure nu n k is actually its stationary distribution. So you let k points go, and you wait a long time, and you see how they are distributed after averaging on the environment, on the genealogical graph. So we want to compute this. It's the same as computing these moments, but it gives you a kind of idea of what happens. It's just a stationary distribution of a Markov chain on a big space. The big space being 1 to n to the power k. So you have a Markov chain. The Markov chain random variable, the Markov chain transition probability, I denote by Q and K, and it's the expected value of the B tensor K, where B was the elementary matrix corresponding to the choice of 2 individuals and 2 parents and 1 killed monkey. Check the tree. So, of course, the problem is that it is a big space. You see, it's a big space. So what do? You have a big space, but you have a situation which is actually very, there is a lot of symmetry in this situation. So what you do is you make it a much less bigger space by dividing by the group of symmetry, which is a permutation of the n elements. It doesn't matter which tree you are on. So when you do this this quotient, you actually your Markov chain actually will live in a much smaller space. What is this space, which I called configuration space, but it's not necessarily. So this space you can describe. It just you describe it by saying how many sites in which there is 1 individual. This I called N1. How many sites in which there are 2, N2, etc. You see. So, for example, if you are looking at k equal 10, you can have 10 individuals on the same site. This you could write like this. Or you could have 1 individuals all in different sites. So k sites with 1 individual. Or you could have one site with 2 individuals and k minus 1 site with 1, etc. You see this is this type of data you keep. So it's not a big space. It has a fixed size. It does not depend on n. See, that's the point. It does not depend on n. So finally, you are in a situation where you have to find a random, an invariant measure, but the space is fixed, and you have a transition probability which depends on n. So it's much better. You feel that you can do it in principle. Should not be too difficult. So you can actually write precisely what is the relation between the distribution on the small space, which I denote it with a tilde, and the configuration I denote by x with a tilde, but doesn't matter too much. So there is a precise relation, which you see here. There is a coefficient which is of the order of n to the k, n to the n to the power, k minus. So what I denote by L is the number of occupied sites. So you see here you have, if I consider a configuration, here you have 1 occupied site. Here you have k, and here you have here Here you have, no. Here you have K. And here. Yeah, here you have. Yeah, okay. Yeah, here you have K-1. Merci. Je savais que je pouvais compter sur vous. So you can translate the condition on moments into this new type of variables, namely the number of occupied sites, etc. And so you end up with what you have to show, namely that an equivalent for the measure, the stationary measure of this Markov chain on the configuration space. If you prove this, you will be done. So how to prove such a result? You see, it's you have a distribution which is about the stationary distribution of a measure which depends on a parameter a transition matrix which depends on a parameter. And so you could think that you can use directly perturbation theory, but it didn't work so well. So there is one method. Actually, our method is in 2 steps. So the first step is to find what is the equivalent. There is an equivalent. That is, what is the order in n of this weight? So of course, it depends on which configuration X tilde you're looking at. I mean, it's not the same weight for this one and for this one. So you have to find the order of magnitude in n, or rather in 1/n, because they are very small, most of them. So to do that, there is a method which is to use the so-called Markov chain tree theorem. So what is it? You can actually, probably many of you know, you can express stationary distribution on a Markov chain on a finite space as a quotient of 2 sums, a sum on rooted trees, the sum on rooted, or the trees which are rooted at the point you're looking at, divided by the sum on all rooted trees. So, of course, there are many trees, so you cannot expect in this way to compute really in this situation where, okay, there is a number k which can be anything, you see, so dimension is fixed, but it is fairly large. But if you look at these weights, so the weights of the trees are given by the transition matrix. Namely, you look at all the edges of the tree and you multiply them. You multiply their weight in the transition matrix. So it gives you a weight for each tree, and you add up, as I said, the sum on the trees rooted at the configuration you are looking at, divided by the sum of all rooted trees of the weights. So then you have, of course, to look at what are these transition matrices, the equivalent of the transition matrix, depending on what type of transition you look at. And it's actually fairly simple, namely when you increase the number of occupied sites, for example, when you go from this to this, yeah, no, it's not, it should be green here, okay. So when you go from this to this, yeah. Here you increase the number of occupied sites, so it's actually quite easy. It's enough to kill at the right place. But you want to decrease the number of occupied sites, you have to actually to choose well, not only the person you kill, but also the one of the parents, or even the two parents, but at least one. So when you increase the number of occupied sites, you have an order which is of the order of 1 over n. And when you decrease, you have an order which can be 1 over n squared or even 1 over n cubed. So it's easy to see that among these trees, they don't have all the same weights, the same magnitude in their weights. And you can clearly see that there is one dominant kind of tree for those who are, when you look at all the trees, you actually have to just look at trees which are rooted where you have the maximal number of occupied sites. And if it is not the case, if you look at some site x tilde, which is not necessarily this 1 to the power k, then you can actually create a path, a red path, that goes from this particular site 1 to the k, where you have k different sites, into this one, and then put all the other branches of the tree along this, this trunk. And this will give you the maximal, the minimal order in 1 over n. So since all terms are positive, all terms which contribute are positive, actually it's enough to have these orders to know what is, that there is actually an equivalent, namely the equivalent you're looking for this one. I mean, the fact that your weight is of the order of n to the power the number of occupied sites. And then you have to find the coefficient. But once you know what is the order of each term, you can just use the definition of the invariant measure. It gives you an equation saying that just that you have the invariance, namely you write, say, invariant distribution, nu q equal nu. You write this by keeping only leading order, and it gives you an equation which is a linear system, and you know the solution already because you guessed it. So you just have to check. So it's not so difficult, elementary anyway, and the only thing you have to be careful in evaluating the coefficient of the transition matrix. See exactly what happens. All right, so that's all for today. Thank you for your attention. And yeah.
So, are there any questions?
So actually, two questions. So first, the 1/2 that you see and the limiting exponential guy reminds of the limit of the Malthusian martingale for a Yule tree, which survives or not. So is it always the case that in your process, you can express this limiting, so the random variable in the end being 0 with probability 1/2, or being this exponential with probability 1/2, which is solution to your recursive distributional equation? Is it always the case that it is given by the limit of the Malthusian martingale on a tree which survives, if it survives?
Well, I explain how you get an M infinity. You see, you just share each time when you have the tree, it determines the tree, determines completely the value of M infinity, because you know exactly how to distribute the weights backward in time. Yes.
And it's at the very beginning that you will decide what is your share in the limiting population, right?
Yeah, when you look forward in time
Yes,
now, yes, it's at the very beginning. Of course, after a while, it does not change very much.
So let me quote you. You are a mathematician and therefore not a physicist, and so you prove theorems. You're not.
I'm trying to.
You try to. You're not a biologist either, so you may change having two parents by having key parents.
Yeah, but then you see, when you try to publish in a biological journal, you get killed. No. Yeah, I tried. We tried, and never again.
Okay. So let me consider this as an answer.
By the way, they are right. They are right. I sympathize with this point of view. But of course, as I said, you have the same model. You can do the same model, but without mentioning child or parents. You can make any mathematical model with M, and then you will have, you can generalize fairly. Yeah. Thank you.
Any other questions?
No, you can.
Is it about the Lacanian things?
Je ne sais pas là.
So you said that when looking for a proof, well, you had a proof, but I found it very nice, but also a little bit not elementary. So did you try before another one before that one?
Yeah, I tried. We tried, of course. Yes, we tried. I told you perturbation theory, just because you are standard method of perturbation theory. But then I hoped I could just apply directly the perturbation theory machine, but it seems that difficult because somehow there is a singularity, you see. So that's why the standard theorem of perturbation theory apparently don't work, but I cannot say that there is not a simpler proof. This proof is elementary. You see, there is nothing difficult in it. It's a really standard Markov chain. The martingale aspect, I think it's there. You cannot, but also this is fairly standard.
Yes, but the space is not so elementary. You
space,
change.
yeah, but there is a symmetry, so it's natural to look to the space anyway. I think even if you want to go beyond this, what we prove here, if we want to analyze further, this is clearly this configuration spaces where things happen. And see, there is an advantage, which you don't want to study things in which you are not in a fixed space. Well, you may want, but it's better. I feel better to be at least in a fixed space and then to have objects which depend on a parameter. But when the space itself is moving, I mean, I'm getting sick.
Okay.
But I'm not saying that there is not a better proof, of course. It's open to your investigations.
Yeah. One more question.
Yeah. Can you perturb the result? I mean, in real life, not everybody is the same. So you want a small perturbation of your result, and then start from your symmetry result.
This is where we might think of using really perturbation theory. Yes, we didn't do it. At least I did not do it. Yeah, no, I don't think we. But yeah, it's reasonable. There are various questions one may ask beyond what I have told today, and some are. But this one we never thought. But yes, could be. Well, many other questions. You see, you can of course think of mutations, and there are many things you can think of in the context of this model.
Okay. Are there any questions in the chat? Okay, well, in that case, I think it's a good point to thank Yves again. And indeed, actually, all the speakers of today for this wonderful day.
Maybe one last thing before calling it a day. I just wanted to know whether there are people who intend to go to the dinner but have not yet registered. Can you raise your hand? Don't be. I mean, we have plenty.